much, Professor Schweitzer. Good evening to everybody. I hope there's still energy left for these two lectures. I remember quite well my university time. The first rows are empty, as it is in a church, because the students don't want to be remembered by their prof if they fall asleep. He could recognize the face in the exam. Okay. We are starting with a very special project, which is at the moment just a little small thing in automotive industry, but you will see that the potential of this project is very, very high, and maybe you will have in your professional time a lot of relation to these to this kind of projects. I've put in smaller letters here the future of mobility, because the future of mobility is something we don't know about. If we did, Audi would be the richest company in the world. So even we don't really know which will be the pathway, and at the moment everybody agrees with the idea that there is not the silver bullet for the mobility of the future, but there are a lot of different alternatives that depend a lot on different markets and needs of the people. Okay, beginning with this very special project, which really is in my almost 20 years of time in the automotive industry, the most interesting issue I've ever worked for, sometimes appears to people a little bit strange. And this is very typical for innovators, that their projects are not always understood at once by everybody. And like here, sometimes you don't really know, okay, and what is the benefit at the moment. So I hope that you will in the end say, okay, I understand that what Mr. Otten told us could be very interesting for the future, and the good thing I can tell you is that this project already works. This is not just an idea for in 20 years or something like this. This is a technology that really works. Maybe not like this early microscope. I'm talking about our power-to-gas project, and this is a photo 1 year old when we were beginning to put into practice this power-to-gas idea. This plant is in the northern part of Germany, because there is a lot of wind energy in the power grid already. And I will tell you what's the idea behind. Maybe you as Austrian students, and maybe students from a lot of parts of the world, have never seen the very big wind turbine parks in the northern part of Germany. When you are there, you will see sometimes that there's enough wind, a lot of wind turbines are running, but 1/3 or even the half doesn't work at all. And people say, it's already broken, or there has to be done maintenance or something like this, or they are not yet in operation because they are very new. No, normally this is not the reason. The reason is that, especially at the weekends, you have a lot of times where you cannot feed in the electric energy into the power grid because there's too much wind. And at the first glance, this is really surprising, because even in Germany, where we have already a lot of wind energy and also PV, photovoltaics, the overall mix of these fluctuating energies is at about 15% of the power of the electricity. And even so, these average 15% are sometimes 60% when there's a lot of sun, when there's at the same time wind, and when the energy demand is low, for example, during the weekends. And so already now with a 15% mix of these energies, we already have problems to integrate the energy into the grid. And when you imagine that we want to have 30, 40, 60, one day 80 or even 100% green energy in our electric grids, you can imagine that you sometimes will have the double of the energy you need. So the idea is to feed in this green energy into the network, and what you cannot feed into the network, instead of cutting off the wind turbines that do not work, they have an efficiency of 0%, to feed this excess energy into an electrolyzer. You all know what an electrolyzer is. Produces hydrogen, oxygen, and then you already have a chemical energy carrier like hydrogen and can make use of it. And for us as members of the car industry, hydrogen is already something quite interesting. You know about the fuel cell cars running on hydrogen. They work already very well. If you drive one, you say, okay, why don't you put it into production? So the technical issue seems to be solved, but at the moment there's no infrastructure, and one big problem is also that the fuel cell car will always be a very expensive car, because you need a battery, you need a fuel cell stack, you need all the electronics to put the power from one system to the other, because a fuel cell car is not only a fuel cell car, it's always also a battery car, a battery hybrid car. Because you need the battery for the dynamics of a car, because the fuel cell is too slow. And you need, for the hydrogen, a very expensive storage system. And at the moment, all the fuel cell cars that are developed in the world are based on a 700 bar fuel cell tank. And so the materials have to be very strong, and so the fuel cell cars will always be quite expensive. So nobody knows when or even if these cars will be a big issue for car industry. But even so, the hydrogen we produce here may be very interesting for automotive industry one day. At the moment, and this is the big idea, the big networks we have, apart from the electricity network, is a natural gas grid. Especially here in Austria, you have really big storage systems for natural gas. And we have these storage systems also in Germany. And so the idea is to use the natural gas grid as the big buffer system for electric power. So we have difficulties to integrate the electric power of these wind turbines and of PV, and we can make use of the natural gas grid if we can feed in something what looks like natural gas, or which does have the same Eigenschaften, properties, thank you, the same properties. And so what we are doing in our power-to-gas plant is producing methane by means of the Sabatier process that combines hydrogen with CO2 in an exotherm process. Mr. Sabatier, 100 years ago, got the Nobel Prize for this reaction of CO2 and hydrogen, and now, 100 years later, we are beginning to put this really into practice. Okay, so you have the energy in the natural gas grid, and you can make use everything out of it. And our idea is to fuel cars with natural gas. In Europe, we have about 1 million or 1.2 million natural gas cars, especially in Italy, in Sweden, but more and more also in Germany and beginning in Austria and Switzerland also. Netherlands has now a big push into CNG cars. So this is one solution to make use of this synthetic methane we have produced here in this machine. Okay. One question is, where does the CO2 come from? You can filter it out of the air. Still expensive, but of course you can get it from a lot of industrial processes, like burning gas or burning carbon or whatever. But even you have biogene CO2 coming from biogas plants. They also have an emission of CO2. And because as this is a form of energy which will play a big role in the future, in the green, hopefully green future, the idea is to make use of this green CO2 for our process. But theoretically, you can make use of any CO2 that otherwise would have been emitted into the atmosphere. And so, as we don't get this CO2 into the atmosphere during the production of our synthetic methane, what we call e-gas in Audi, the emissions of the car are not so important anymore, because the only carbon source here is coming from the CO2 that doesn't get to the atmosphere anymore. And so you can imagine that it's a virtual circle of CO2. So we are making use of CO2 as a raw material to produce a fuel, and so running this car is almost climate neutral. Okay, coming back to another car we offer. I will come back to the power to gas idea after this. A lot of people, as we have begun to make or to put this idea into practice, a lot of people said, "Oh, it's because Audi does not want to have electric cars, or they are not able to produce them, or whatever." In order to avoid this misunderstanding, I always present also our Audi A3 e-tron that's on the market. It's a plug-in hybrid. I don't know if I give more information. No. You can go 40 or 50 kilometers in a pure electric mode with this car, but you have still a combustion engine in order to make use of this cars also for longer trips. So you can run emission-free in the city, but it does not have to be the second or third car of your family. It can be a first car of a small family, for example, and because you can use this car as any hybrid car without being dependent on the electric energy from the grid. But you can run also this car all the year completely with electric energy if your trips are not longer than, let's say, 40 or 50 kilometers. This is our first step into electric mobility. Within the Volkswagen Group, you know, Audi is part of the Volkswagen Group. We also have pure battery electric cars like the e-Golf and the e-Up. But in Audi, we are concentrating at the beginning with plug-in hybrids, because we say the probability that these cars are better accepted by our customers is higher. And of course, even if you run this car in the electric mode, or if you have a pure electric car, the question is it really better for the climate than a conventional car? And we know, I hope that we will have, we did a life cycle assessment, and I think you have seen this in newspapers also. If you run an electric car by carbon power or fossil energy, the climate effect is not positive. If you use black carbon or brown carbon, it's even negative if you compare it to a combustion engine car. So the benefit of an electric car is only there if you really have a big part of green energy to fuel it. And so our CEO, Mr. Stadler, already 3 years ago said, okay, if we begin to push electric cars into the market, then we will do also some efforts to establish more green energy in the electric grid, because otherwise we just you just put the green energy from other parts of the market, and there's no benefit at all for the environment. Okay, so the Volkswagen Group also has investments in PV parks and wind parks, but beginning with this kind of investment, you feel directly the challenges also. And these are the challenges I have told you in the beginning. How can we integrate in the best way these energies, these strongly fluctuating energies into the grid? And this is a simulation of the Fraunhofer Institute in Germany. They imagined maybe the year 2040 or something like this, with 78% of the energy production, of the electricity production by means of green sources. Here 78% in this simulation. And what happens to the grid if you let run the wind turbines all the time? It wouldn't work. This is the nightmare for every grid manager in the electricity sector, because what you need here is a flat line at zero. The demand and the offer of electricity must be exactly the same. And what you see here is the residual load. So the question that answers this graph is, how many conventional plants do you need, and which performance should they have if you don't want to have blackouts? So this is the red curve here. So you sometimes have these peaks where you need more energy than wind and PV are offering. And for these situations, you still need other kinds of power generation, like, for example, gas power stations. But what you also see is that during a lot of times you have an excess of energy, and all this energy you have to cut off, because if not, you destabilize the electric grid. And the question is, do you throw away this energy, or do you try to store it in any system? But as you see, these are huge amounts of energy. If you make an integral of this curves here, you come to this amount of energy, almost 200 terawatt hours a year. I think this is almost the third part of the overall energy we need today in the electric grid in Germany during a year. So it's worth thinking about it. And here, in this simulation, they also have put as a premise that there is no problem to transport the energy. So there is a perfect electricity grid, which is far away from the reality we have now. You maybe have heard about the discussion in Germany about the additional electric grid lines, and people don't want to have it. Maybe 50 kilometers away, but never close to my home. But even if we have a solution for this, you have in the end this situation. Okay, and the idea is, how can we manage to store at least a part of this energy? You will not be able to get every peak here, but maybe to cut it off here at this line by means of any storage system. And here you can see what we already have. Do you see this very fine brown line here? This surface, it's in order to see it, it's even bigger than in reality. This surface is what we already have in form of batteries and pump storage systems to store energy. We have some systems in the grid, especially here in Austria. You have a lot of pump storage or some pump storage facilities. But in Germany, we just have this capacity, nothing compared to what we need here. There you have 3 weeks of excess energy. And the natural gas grid offers a capacity of this size, so completely different. And the big idea of power to gas is to combine electric grid and natural gas grid in order to have this big buffer. Okay. At the moment, nothing to do, anything to do with automotive industry. There are other storage alternatives. I told you about these pump storage lakes, but they give, if you want to give energy to the consumption in Germany, 1 hour, and then they are empty. The idea to make use of electric cars and their batteries is a very good idea, because these batteries give very fast response and they have a big performance. So in order to control rapid peaks in the electric grid, this is an interesting solution, and we should follow this pathway. You heard maybe the smart grid idea. They call it smart grid, and part of the smart grid is to make use of the batteries of electric cars. But even if all the passenger cars in Germany were electric cars, and the owners of these cars were ready to give half of their range to the public in order to make use of the battery as a buffer, the capacity to store and to give back energy is about 6 hours. And the natural gas grid, compared to this, is in the region of months and not hours anymore. So completely different. There's a question. The simulation comes from the actual natural gas grid without any additional construction. So yes, the idea it's just to tell you the dimension. The idea is that, and this is also a theoretical idea, if we don't get any additional gas from Russia or from Tunisia or wherever, we could cover the electric power need of Germany during 2 months just from the natural gas grid by means of burning gas and making electric power out of it. This is the idea. Of course, we need the gas also for other purposes. So in reality, you don't have these 2 months, but you have maybe 6 weeks or 4 weeks. And if you get back to this graph, if you can store 2 or 3 weeks, you get this, you get this, you get this, you get this. Okay? Okay, this is the idea. And these are the partners Audi has been working with to establish the world's first power-to-gas plant that really combines electric grid and natural gas grid. What I've shown you here. This is the same plant I showed you in the beginning in a photo, just a CD design here. Here you see the hall where we have the electrolyzers in. This is the methanation unit. You all know the catalyst, maybe those who have an own car or know the car of the parents or friends. You have a catalytic converter in your car that converts hydrocarbons and carbon monoxide and so on into CO2. And you can imagine this also. Huh? It's a big tube where hydrogen and CO2 go in, and in the presence of a catalyst, they combine to synthetic methane, CH4. In order to feed the synthetic methane into the natural gas grid, we need, of course, compressors. But a lot of times we don't need them because we feed this green gas into a local gas grid where you just need a pressure of 1 bar, and in the process we have more than 1 bar. So there's no additional energy needed. Just in the summertime, when the local natural gas grid does not need so much energy, we have to push our stored energy into the transportation grid where we have about 40 bars, and then we need the compressors. So this is the view of the power-to-gas plant, but just this here is the power-to-gas plant. All the rest here is a 10-year-old biomethane plant, and this is very interesting because they don't just give the CO2 to us. As we have energy losses, I will show you in which size, we give our excess heat to this biomethane plant. They need heat for different purposes. For example, at this place here, where they get the biological waste, they have to do a sterilization at about 80 degrees during 1 hour to kill the wrong bacteria that could get in, and in order to make survive the good bacteria that make the fermentation process there. So they need energy here, and they also need energy because this is not a biogas plant that turns the energy directly into electric power, but feeds in biomethane in the natural gas grid. And then this energy can be burned when electric energy is needed. In Germany, there's a shift now from the old biogas plants that produce 24 hours energy, not knowing if the energy is really, if the electric energy is really needed, to biomethane plants that put the biomethane into the grid, and then you can burn this energy in the situations when you really need it. Okay, and for the separation, for the purification of the raw biogas to biomethane, you also need heat. And so this combination of a power-to-gas plant with a biomethane plant is very intelligent. But it's not necessary. You can make use of any CO2 and make use of the excess heat in other ways. But this is just one good example we have started with. So I skip this because this is once again bird's perspective. More interesting maybe the photos. This is one of the 2 megawatt electrolyzers, more or less as big as a locomotion and also as heavy, about 70 or 80 tons. And this is the methanation unit. Here you can maybe see a little bit the tubes where the methanation process runs. So some data about it, or maybe the most interesting data is this here. The efficiency of the power-to-gas process from electricity to methane is at about 54% in this first plant. We will be able to increase this in the future with better electrolyzers, but at the moment we are more or less at this size. So the other 46% are going anywhere in form of heat. And what is very interesting, we have put here an operation time of 4,000 hours a year. 1 year has 8,760 hours. So we have put here 4,000 hours, which means almost 45% of the year this plant would run. And this is already a reality in Germany. We have prices for electricity lower than 3 cents per kilowatt hour in the electricity bourse in Leipzig. What means that there is a very low demand for this energy. So by the integration of our green power, we have as a result that at many times of the year the energy is very cheap. Because of course a wind turbine, when it runs, it runs. You don't have to put any carbon or gas, which makes you a cost. So the, how do you say, Grenzkosten? The differential cost for a running carbon plant is always the price for the carbon itself, or in a gas plant for the gas itself. But if you use wind energy or sun energy, it's zero. And so at many times of the year, the energy in the electric grid is already very low. So this is the efficiency pathway from the wind turbine, electric power, okay, let's say 100%. A very good electrolyzer would be at 75% efficiency. This will happen in the close future. At the moment we are rather at 65, maximum 68% efficiency with our electrolyzers we have today. So there you have, here they have put waste heat. Interesting, waste heat, because it's a low temperature loss. And normally in industry they say low temperature heat is difficult to make use of. Okay, the methanation process does have high temperature losses, and there you can put a lot of industrial purposes, or use it for a lot of industrial purposes. So, but let's put it apart at the moment, and then you have here about 60 to 65% synthetic natural gas at that point. If you come to the idea to store this energy and to make later on electricity out of it, to cover the red peaks you have seen in the beginning, then you have once again losses in the natural gas power plant, of course. The best ones are at the moment at 60% efficiency from gas to electricity. So in the end you will have at a maximum 35 or 40% from electricity to electricity. But if you make use of the heat here, high temperature heat, and also here, then you can come to 50 to 60% combined power. And in reality, in our first of the world power-to-gas plant in Werlte, we even make use of part of this low-temperature heat by means of some tricky ideas. And I show it here. Here you have the electrolyzers, and they have this low temperature losses at 65 or 70 degrees. But we need here for the sterilization process in the biomethane plant 80 degrees. And at an efficiency of 68%, of course, this is a lot of heat, but at low temperature level. But we combine here the high temperature circle coming from the methanation process, 170 degrees. We make use of this high temperature heat in the separation process for the CO2 that is needed in the biomethane plant. But at the same time, we give some of the heat to the low temperature circle and put this excess energy we have here to the low temperature circle to push it from 65 to 80 degrees Celsius. And this way we can make use also of the big losses that come from the electrolyzer. So if you think twice, sometimes in industrial processes, you find very clever ideas that may help you to get rid of old ideas. A lot of people say low temperature heat is lost, but not necessarily. This is a measurement graph of the running power-to-gas plant in order to show how much time does it need to make the methanation process run. And we are talking here about some 5 or 6 minutes, and then we have already here a concentration of methane at more than 90%. So we have the quality we need to push it directly at any time into the natural gas grid. So it does not need 1 hour or 2, just some minutes. This is important in order to avoid losses. And this is simulations we have made on the base of real data from the electricity boards in Leipzig, according to the prices you have to pay for the electricity. And always when the prices are lower, here you have the prices, are lower than 3 cents per kilowatt hour, then we switch the power to gas plant on, because then electric energy is very cheap. And so we have a simulation, how will this power to gas plant run? And we see that we normally just have to switch it on or off 2 times a day. This is a very interesting result because, of course, it's better for a big industrial plant to run sometimes steadily and not to be switched off every 5 minutes or 15 minutes. Okay, coming back to the cars. All this is energy sector. Now we are talking about the cars, but first we have a question here. Mm-hmm. But this is a very low effect, because the maintenance cost of a wind park is very low, and it rather depends on time than on revolutions of the wind turbines. And and normally also with wind turbines, if you have to switch them off and to even have a braking process to shut it off, then maybe you have more disturbances to the system than in a steadily running wind turbine that doesn't have to be decelerated. So this is not a big effect at all. This story seems to be nice. We get cheap energy from the electric grid. We make use of CO2 that otherwise would go to the atmosphere. We use an existing infrastructure, the natural gas grid, and have energy almost for free if we hadn't the big cost for the electrolyzers and so on. So sounds very, very good, and we could convince also our board in Audi by this idea. But we didn't have any car that could run on the energy we have fed into the grid. Until last year, we didn't have any CNG car in our portfolio in Audi, but now we have. So parallel to the development of the power-to-gas plant, we also developed this car. And this is a combustion engine car, yes, but optimized for natural gas or biogas or synthetic gas for methane by means of different measures in the engine, in the turbo engine, for example, a smaller turbo and so on. And of course, we had to develop a second fuel system, because this is a B-fuel car. We still have a normal fuel tank for gasoline, because we don't have enough stations, for example, in Spain or in France. If you want to make a vacation trip to these countries, it's very nice to have still a gasoline tank. And just about 7% of the gasoline stations in Germany have a CNG station also. Here in Wels, I've seen you have one CNG station, but maybe 20 or 10 normal fuel stations. And already running on fossil natural gas, you have very low greenhouse gas emissions here. And you have also, because the engine is very efficient, quite interesting range, about 400 kilometers just running on natural gas. But if you make use of the e-gas, then you have a better effect. We have made here a complete life cycle assessment, taking into account also the production of the cars. Here you see a battery electric car has a higher burden in the production phase. You see here also that a CNG car is better than a gasoline-fueled car. We also take into account here the production of the fuel. For example, in a gasoline car, you have the transportation of the crude oil, you have the refinery process, and so on. All this has to be taken into account in a life cycle analysis. And you see here a normal CNG car is already better than a gasoline car. And if you run it on this e-gas, it's much, much better, because in the production process of the fuel, you have a negative effect, or a negative emission of CO2, because you avoid emission from another plant. And then the CO2, of course, the same amount is emitted by the car, but this is neutral. And you just have the effects of the pressurizing of the natural gas for the 200 bars fuel tank and so on in this life cycle analysis. But in the end, you are as good as battery electric car running just on wind energy, because here you have better efficiency, but you also have the higher burden of the production of the battery and the complete car in case of a battery electric car. So very interesting in terms of greenhouse gas emissions and overall greenhouse gas emissions. That's the question. Very good question. At the moment, we don't have the problem that there is not enough CO2. But of course, and there sometimes is a misunderstanding. Some guys from automotive industry say, "Oh, that's perfect. We don't need any battery electric cars anymore." But that's the reason why I said we don't have here the silver bullet to solve every problem. Because of course, if you produced wind turbines, extra wind turbines, to fuel these cars, you needed 4 times more wind turbines or PV plants compared to a battery electric car. So this is a way to make use of excess energy, especially, the scarcity of excess energy is the bigger problem than the emissions of CO2 that you need to produce the fuel. And even in the future, if you have cut off all the fossil power stations, there would be enough biogene CO2 coming from sewage stations, Kläranlagen, from biomethane plants and so on. So this is not a big issue, and you even can get CO2 out of the air if you want. Just more expensive. So what's very interesting is in this technology for automotive industry is that you have a positive effect for more green power in the electric grid. This is good for the electric cars because, as we have seen, electric cars only are green when they run on green power. You have a solution, a renewable solution for hydrogen cars, and you can already today, with an existing infrastructure and with cars that are not more expensive than a diesel car, run climate neutral on the longer distance as an addition to the electric car. So we have to see this solution as an addition, not as an alternative to electric driving. This is a very important message for us. And this is for reading it afterwards. You will get the presentation. Why don't they just produce hydrogen? That's a question they often ask us. Here are some reasons. And some reasons I told you already. And yes, this is the message. We have a solution, not just for short distances, battery electric car. We have a green solution also for about, in Germany, 8 million cars that could run with the energy we have there. So this is we cannot cover the complete car park with the solutions, but we are talking about some million cars that could be fueled with this kind of fuel. And yes, we have a very important technology to make more, or to make faster the process of going to green energy in the electric grid. Last slide. I've just told you at the moment it does not make sense to produce additional green energy from wind turbines or PV to fuel these cars. But if you did, you just needed this surface of PV plants, and not in Africa, but in Europe, with the sun intensity of Europe, to fuel all the passenger cars in the world with the efficiency of these cars today. So, in the theory, it is a solution, and this is the big point. If you compare it to biofuels, you have a 20 times better use of area. At the moment, we are producing big amounts of bioethanol and so on, and you need a lot of space. And you already know about the competition between food and fuels. You are running into ethical problems. Here you need 20 times less space, and so it's an interesting solution for the future, where we already have a lot of green energy coming from PV and so on. Additional stuff to read. At the moment I will stop. Maybe you have some more questions, and I hope you will see this in the future and will maybe be part of this future where we put more brain and energy and skills into this kind of ideas. This is just one idea. I think there are a lot ideas that go into this direction to combine the energy sector, the mobility sector, and also the sector of the households, where maybe also heat is needed. Thank you very much.